This paper tackles a fundamental problem with LLMs in robotics. They generate plans that sound good, but may not work in reality. The author's key innovation is inverse prompting, a multi-step reasoning approach that validates plans by checking if inverse actions can restore the system to its original state. This self-correction approach produces more interpretable feedback, resulting in better task planning without requiring external knowledge or predefined error sets. Figure 1 illustrates the progression of validation approaches in robot task planning. While the no-validator approach is straightforward but error-prone, external validators require predefined rules or costly external knowledge. Self-correction methods allow LLMs to identify their own errors, but lack structured reasoning. The author's inverse prompting method elevates self-correction by incorporating multi-step reasoning and explicit state verification, enabling more effective feedback while maintaining self-sufficiency. Figure 2 provides a concrete example of how inverse prompting enhances feedback quality. In the ball-moving domain, standard prompting incorrectly identifies the error as "ball 1 is not in room," when the actual error is about robot location. Inverse prompting reveals this by 1. Computing the inverse action, drop ball 1, 2. Determining the expected state after that inverse action, and 3. Comparing it with the original state to identify the discrepancy. That robot 1 is in room 1, not room 2. This multi-step reasoning leads to more accurate error identification. Figure 3 shows how inverse prompting fits into the broader robot task planning framework. The process begins by translating natural language instructions into a planning domain definition language, PDDL formulation. The LLM then generates an action sequence, which undergoes validation using inverse prompting. If deemed feasible, the robot executes the actions. Otherwise, the system generates feedback to refine the plan. This cycle continues until a feasible plan is identified or a maximum attempt limit is reached. Notes: Section 3 details the inverse prompt methodology. The approach treats state transitions symbolically and validates them by checking if inverse operations restore the original state. The 3 key validation steps are verifying the resulting state of each action, applying the inverse action to check if it restores the original state, and confirming the final state matches the goal. This leverages the inherent inverse relationship between actions like pick and put down to verify logical coherence without external validators. Figure 5a demonstrates how inverse prompting performs in real-world robotics. In the blocks world experiment, the robot needed to stack blocks in a specific order. The initial plan included an infeasible action to unstack B4 from B3. The inverse prompting method provided detailed feedback about the error, resulting in successful replanning. In contrast, standard prompting detected the initial error but produced unhelpful feedback, leading to another infeasible action, pick up B1, that caused a collision. This practical example highlights how more detailed reasoning leads to better task execution. Inverse prompt represents a significant advancement in self-corrective task planning with LLMs. By incorporating multi-step reasoning through inverse actions, it achieves substantially higher success rates while requiring fewer correction attempts. The method's strength lies in its ability to generate explicit, interpretable feedback without external validators or predefined rules. The authors demonstrated its effectiveness in both benchmark scenarios and real-world robot tasks, showing particular advantage in handling unexpected failures that often occur in real-world applications.